Moscow, 1962. Physicist Pyotr Ufimtsev published a technical article entitled Edge Wave Method in the Physical Theory of Diffraction. In its dense pages of mathematical equations, Ufimtsev described how electromagnetic waves bounced off flat surfaces and how these returns could be calculated and predicted. The work was theoretical, abstract, seemingly without immediate practical application. Soviet authorities considered it harmless and classified it as basic research with no strategic military value. Ufimtsev's superiors allowed his work to be published openly. The print run was modest. Barely 6,500 copies circulated in Soviet academic circles. USSR engineers skimmed the document, assessed its implications, and came to a conclusion that would change the course of modern air warfare. Ufimtsev's mathematics was interesting from an academic point of view, but useless for real-world applications. The radar worked perfectly well as designed. Why complicate things with complex geometries based on abstract equations? What the Soviets failed to understand was that they had just discarded the master key to invisibility. On the other side of the world, in California, a mathematician named Dennis Overholser was working for Lockheed Advanced Development Projects, better known as Skunk Works. It was 1975, and Lockheed's Special Projects Division had received an extraordinary request from DARPA, Defense Advanced Research Projects Agency, to design an aircraft that would be invisible to radar, not only partially difficult to detect, but invisible. The problem seemed impossible. Conventional aircraft reflected radar waves like mirrors reflect light. Predictable, bright, impossible to hide. American engineers had tried for years to reduce radar signatures through refined aerodynamic shapes, but the results were incremental, insufficient. They needed a fundamental breakthrough, not incremental improvements. Overholser discovered Ufimtsev's work in an English translation that the Air Force had commissioned almost by chance as part of its routine review of foreign technical literature. What the Soviets had dismissed as theory without practical application, Overholser saw as the Rosetta Stone of stealth technology. Ufimtsev's equations not only explained how electromagnetic waves bounced off flat surfaces, they also provided a mathematical method for predicting exactly how much radar energy would return to the emitter from any given angle. The revelation was immediate. If he could calculate radar returns, he could design surfaces that would reflect those waves in any direction, except back to the source. Invisibility wouldn't require exotic materials or science fiction force fields. It required geometry. It required flat facets, oriented with mathematical precision, to deflect radar waves like mirrors deflect light, sending the returns bouncing off into empty space instead of toward enemy receivers. Overholser developed a computer program called Echo 1, based directly on Ufimtsev's mathematics. Echo 1 could model complex surfaces composed of multiple flat facets and calculate the resulting radar cross-section, the RCS, radar cross-section, the ultimate measure of how visible an object was to radar. The lower the RCS, the more invisible the aircraft. The simulation results were extraordinary. Echo 1 predicted that an aircraft designed with carefully oriented angular facets could have an RCS thousands of times lower than a conventional fighter jet. An F-15 Eagle had an RCS of approximately 25 square meters. Echo 1 suggested that a faceted design could achieve an RCS of 0.01 square meters or less. It wasn't perfect in visibility, but in practical terms, it was indistinguishable from radar invisibility of the time. In 1976, DARPA launched the Experimental Survivable Testbed, XST competition, inviting Lockheed and Northrop to propose stealth aircraft designs. Lockheed presented a radical concept, a completely faceted aircraft that looked like it had been assembled from pieces of metal origami. There were no smooth curves, no traditional aerodynamic lines. The design, nicknamed the Hopeless Diamond, for its angular, seemingly unflyable shape, deliberately sacrificed conventional aerodynamics on the altar of RCS reduction. The Air Force was skeptical. The design seemed to violate all known principles of controlled flight. The flat facets and sharp angles would generate turbulent airflow. Stability would be problematic. Control would require preferred fly-by-wire systems that were only just beginning to become viable. But Echo One's predictions were unequivocal. The hopeless diamond would be virtually invisible to radar. In 1977, Lockheed received authorization to build 2 demonstration prototypes under the classified Have Blue program. The cost, $37 million. The location, Area 51, Nevada, the top-secret base where the United States tested its most sensitive projects. The objective, to demonstrate that a faceted aircraft could fly and, more importantly, that it was truly invisible to radar. Have Blue's first flight occurred in January 1978, piloted by veteran test pilot Bill Park. The aircraft measured just 14 meters in wingspan, weighed 5,670 kilograms, and was powered by 2 General Electric J85 engines, the same ones that powered the T-38 trainers. It wasn't big, it wasn't powerful, but when radar technicians on the ground activated their tracking systems, something extraordinary happened. They detected nothing. The operators checked their equipment repeatedly, convinced that something was wrong. The radars were operating correctly. The problem was that the Have Blue simply didn't return enough signals to generate a detectable return. A real aircraft, flying directly in front of state-of-the-art radars, was invisible to them. Ground-to-air radar tests confirmed what Echo One had predicted. The Have Blue's RCS was extraordinarily low, orders of magnitude lower than any operational aircraft. The results exceeded expectations. The technology worked. The faceted geometry, based on Ufimtsev's mathematics, could really make an aircraft invisible. Have Blue flew 36 test missions before both prototypes were lost in crashes, the first in May 1978, the second in July 1979. But the tests provided enough data to justify the next step, an operational fighter aircraft. In November 1978, even before the Have Blue program concluded, the Air Force authorized Lockheed to develop the F-117 Nighthawk under the classified Senior Trend program. The F-117 was essentially a larger, more refined version of the Have Blue. It measured 20 meters long with a 13-meter wingspan. It was powered by 2 General Electric F-404 engines, the same ones that powered the F/A-18 Hornet. The aircraft could carry 2,268 kilograms of weapons in 2 internal bays. To maintain its stealth signature, no weapons could be mounted externally. Its mission, to penetrate deep into enemy territory, evade integrated air defenses, and destroy high-value targets with surgical precision. The F-117's first flight occurred on June 18, 1981, just 31 months after contract authorization. Test pilot Hal Farley completed the maiden flight without incident. During 1981 and 1982, 5 additional full-scale development aircraft joined the test program. By 1983, the F-117 had achieved initial operational capability, but the program remained classified under the strictest secrecy. The F-117's existence wasn't publicly revealed until November 1988, more than 7 years after its first flight. During that period, the 4,451st Tactical Group operated Nighthawks from the Tonopah Test Range in Nevada under extraordinary security conditions. Pilots flew only at night. The aircraft were kept in specially constructed hangars during the day. Personnel were prohibited from discussing their work, even with family members. The phrase stealth fighter became an urban legend among aviation observers, but concrete details remained elusive. The world finally saw the F-117 in action during the U.S. invasion of Panama in December 1989. 2 Nighthawks bombed a Panamanian Defense Forces barracks in Rio Hato. But it was during the 1991 Gulf War that the F-117 definitively demonstrated its revolutionary value. On the night of January 16th to 17th, 1991, as Operation Desert Storm began, F-1 11s led coalition airstrikes against Iraq. Baghdad was protected by one of the densest air defense systems in the world. Approximately 3,000 anti-aircraft guns, 60 surface-to-air missile batteries, and multiple layers of search, track, and weapons guidance radars. Iraqi military planners had studied U.S. capabilities and were confident that their integrated defenses would inflict significant losses on any attacking air force. Iraqi radar operators scanned the skies that night, looking for the first indications of approaching aircraft. They detected nothing. The F-17S penetrated Iraqi airspace completely undetected, navigating using inertial navigation systems and GPS, illuminating targets with laser designators, and dropping precision-guided bombs on command and control facilities, communication centers, and fortified bunkers. The explosions began without warning. Iraqi defenders fired frantically into the empty sky, launching thousands of anti-aircraft rounds without a clear target. Surface-to-air missiles soared high without effective radar guidance. Anti-aircraft artillery laid arcs of tracer fire that lit up the night, but there were no visible aircraft to shoot down. During the 43-day air campaign, F-117Es flew more than 1,250 sorties, dropped more than 2,000 tons of munitions, and flew more than 6,900 combat hours. Despite operating in the most dangerous air environment of the war, penetrating defenses specifically designed to shoot down aircraft, no F-111s were hit, none were shot down, and none suffered damage from enemy fire. Pilots reported hearing anti-aircraft artillery blasts around them, seeing missiles pass in the distance, and observing the night light up with tracer fire. But they were never targeted. Iraqi radar systems simply couldn't see them. Missile operators had no tracking signals. Gunners fired blindly, hoping to hit something by pure statistical probability. The F-17's effectiveness was devastating. Despite accounting for less than 3% of total coalition sorties, Nighthawks attacked more than 40% of strategic targets during the first 24 hours of the war. Coalition commanders assigned the F-117 the most critical and best defended targets, confident that stealth and visibility would allow them to accurately hit what other aircraft couldn't, without prohibitive risk. Iraqi military planners, many of them trained by Soviet advisors, had based their defenses on Soviet integrated air defense doctrine, multiple layers of mutually supporting systems, redundant radar coverage, coordinated fire. This doctrine had worked effectively against conventional aircraft for decades. The Israelis had suffered significant losses against similar defenses in 1973. The Americans had lost numerous aircraft over North Vietnam in the 1960s and 1970s. But Soviet doctrine assumed that attacking aircraft were visible to radar. The entire defense architecture depended on early detection, continuous tracking, and radar-based weapons guidance. When the F-117 denied that fundamental detection, the entire system collapsed. Without detection, there was no tracking. Without tracking, there was no weapons guidance. Without weapons guidance, defenses were firing blindly at an invisible enemy. The historical irony is profound and sobering. The Soviets had the math. Pyotr Ufimtsev had developed the fundamental theory that made stealth technology possible. But Soviet engineers and commanders failed to recognize its military value. They saw abstract equations with no practical application. They didn't imagine that those equations could be transformed into aircraft that would redefine air warfare. The Americans, in contrast, immediately recognized the revolutionary potential. They took the mathematics that the Soviets had freely published, transformed it into computational algorithms, designed faceted geometries impossible without that mathematics, built prototypes, tested the concepts, developed operational aircraft, and ultimately deployed a capability that gave the U.S. Air Force an unprecedented tactical advantage. The development of the F-117 represented more than brilliant engineering or clever application of Soviet mathematics. It represented a fundamentally different philosophy of military innovation. The Soviet mindset tended toward technical conservatism, relying on proven systems, distrusting radical concepts, prioritizing mass production over risky technological leaps. The American mindset, embodied in organizations like Skunk Works, embraced disruptive innovation, accepting technical risks, exploring radical concepts, prioritizing technological advantages even if they required unconventional approaches. This philosophical difference had lasting strategic consequences. While the United States was developing the F-117, it was also working on the B-2 Spirit, a stealth strategic bomber that also utilized Ufimtsev's mathematics. Northrop used similar computational methods to design the B-2 with continuous curved surfaces instead of flat facets, demonstrating that stealth technology could evolve beyond the angular designs of the first generation. The Soviets eventually developed their own stealth technology programs, but they arrived late. When the USSR collapsed in 1991, its stealth programs were still in preliminary stages. Russia inherited these efforts and eventually produced aircraft like the Su-57. But decade after the United States had operated the F-117 and B-2. The stealth technology demonstrated by the F-117 transformed strategic thinking about air power. Before the F-117, dense air defenses could deny access to airspace, forcing attackers to accept significant losses or avoid well-defended targets. After the F-117, no air defense could guarantee absolute protection. Stealth aircraft could penetrate even the most sophisticated systems, strike critical targets with precision, and escape undetected. This capability altered calculations about deterrence, escalation, and crisis control. Nations facing the possibility of stealth attacks could not rely on their defenses to protect critical infrastructure. Military leaders had to assume that key installations were vulnerable no matter how well defended they appeared. This fundamental vulnerability changed regional and global power dynamics. The F-117 operated until 2008, when the Air Force officially retired it from active service. By then, it had been surpassed by fifth-generation designs like the F-22 Raptor and F-35 Lightning II, which integrated stealth technology with supercruise, supermaneuverability, and advanced sensor fusion. But the F-117's legacy endures. It was the first. It was the concept demonstrator that proved that stealth was possible, practical, and devastatingly effective. The F-17's technical specifications reflect the compromises necessary to achieve extreme stealth. The aircraft had a top speed of just Mach 0.92, deliberately subsonic to minimize infrared heat and acoustic signature. Range was approximately 1,720 kilometers, with aerial refueling extending that significantly. The service ceiling was 13,716 meters. The crew was a single pilot. Armament was limited to two 2,000-pound laser-guided weapons, or air-to-surface missiles in internal bays. These specifications seem modest compared to conventional fighters. An F-15 was faster, more maneuverable, and could carry more weapons. But the F-15 was visible. The F-117 was not. That unique difference overrode all other considerations when the mission required penetrating integrated defenses and destroying critical targets that would determine the course of a war. F-117 pilots operated under unique procedures tailored to the stealth mission. They flew exclusively at night to minimize visual detection. They maintained strict radio silence during penetrations. They navigated using inertial systems and GPS without emitting active radar signals. They illuminated targets with laser designators only in the final moments before weapons impact. Every aspect of their tactics was designed to exploit invisibility while minimizing any action that might compromise that advantage. Training was rigorous. Pilots practiced precise navigation without visual references, delivery of surgically precise guided weapons, and emergency procedures specific to the F-17's unusual flight characteristics. The aircraft was inherently unstable, requiring constant input from the fly-by-wire control system. Pilots had to rely completely on automated systems while maintaining situational awareness in high-threat environments without the benefit of active search radar. The culture within F-117 units reflected the special nature of their mission. Pilots were selected from the Air Force's finest airmen. Safety was absolute. Even after the program became public, specific details about capabilities, tactics, and vulnerabilities remained classified. Pilots developed intense professional pride in operating a unique aircraft that gave them capabilities no other airman possessed. F-117 maintenance was extraordinarily demanding. The faceted surfaces were coated with radar-absorbent materials that required constant inspection and repair. Any damage to these coatings compromised the stealth signature. Technicians worked to exceptional standards of precision, aware that minor errors could increase the RCS enough to make the aircraft detectable. Special hangars protected the aircraft from the elements and hid details of their construction from reconnaissance satellites. The F-17's operational costs were significant. Each flight hour required many hours of maintenance. Stealth materials were expensive and required frequent replacement. Specialized systems required highly trained technicians. But commanders considered these costs justified. The F-117 could achieve effects no other aircraft could replicate. Its value was not measured in costs per flight hour, but in its ability to change strategic outcomes. The retirement of the F-117 in 2008 marked the end of an era. The aircraft had served for 27 years, flown in 3 wars, Panama, Gulf War, Kosovo, and had never suffered a combat loss except for a 1999 incident over Serbia, where an F-117 was shot down by an SA-3 missile under exceptional circumstances, involving a combination of factors including predictable flight paths, an exceptionally innovative missile commander, and specific operational conditions. Even that single shootdown confirmed rather than refuted the effectiveness of stealth technology. The Serbs needed near-perfect conditions, detailed intelligence on flight patterns, an SA-3 system operating in non-standard ways, and considerable luck to achieve a single kill after dozens of F-111s had flown hundreds of sorties over the same territory for weeks. No other anti-aircraft system achieved a confirmed kill of the F-117 in more than 2 decades of combat operations. The history of the F-117 is fundamentally a story of recognizing value where others failed to see it. Pyotr Ufimtsev developed brilliant mathematics that his superiors considered academically interesting, but militarily useless. The Americans recognized that same mathematics as the key to a revolution in air warfare. This difference in recognition and application of scientific innovation had consequences that reverberated through decades of strategic competition. Ufimtsev eventually emigrated to the United States in the 1990s, worked at UCLA, and received recognition for his fundamental contributions to stealth technology. He expressed surprise that his theoretical work had such profound applications. He had never imagined that equations on electromagnetic wave diffraction would transform military aviation. The Soviet engineers who dismissed Ufimtsev's work made a decision that seemed reasonable at the time. The mathematics was complex. The practical applications were not obvious. Resources were limited. Prioritizing mass production of proven systems over speculative research into faceted geometries seemed sensible. But that reasonable decision had lasting strategic consequences. When F-111s flew over Baghdad in 1991, invisible to Soviet radars operated by Soviet-trained technicians, the lesson was clear. Radical technological innovation could deliver decisive advantages. Mathematics mattered. Basic science mattered. Recognizing the potential of abstract research mattered. And a willingness to take risks in developing radically new systems could produce capabilities that fundamentally changed the character of warfare. The F-117 Nighthawk began as equations in a Soviet technical paper that no one considered important. It morphed into a classified program operating from secret bases. It culminated as an aircraft that penetrated the world's most formidable defenses, destroyed critical targets with impunity, and demonstrated that invisibility was not fantasy, but a reality achievable through geometry, mathematics, and brilliant engineering. Every time an F-117 disappeared from enemy radar screens, every time a pilot penetrated integrated defenses undetected, every time a guided bomb destroyed its target while defenders fired blindly into the empty sky, a simple truth was validated. In modern warfare, seeing the enemy isn't enough if the enemy has learned to become invisible. And it all began with a Soviet physicist whose mathematics was ignored in his own country but embraced by adversaries who recognized its revolutionary value. The sky over Baghdad in January 1991, lit by anti-aircraft fire tracing random patterns against an invisible enemy, told a story of innovation, application, and the consequences of recognizing or ignoring the transformative potential of scientific research. Soviet engineers dismissed the idea. American engineers transformed it into reality. And the F-117 became invisible, forever changing the nature of air warfare.